So today is section 3.4, real zeros of polynomial function. And so we want to look at finding the zeros of a polynomial. So here's a quick overview of what we talked about. Please keep in mind that a couple of the long division technique and the synthetic division technique, I have prepared separate videos for those. So I'm just going to go through them fairly quickly in this video. From the fundamental connections that we know, that a 0k is related to a factor of the polynomial in this fashion. So if I have a 0, then I know that this kx minus k is also a factor. We can use the factor, so we can factor a polynomial into linear factors, and then we can find all the zeros. So we're going to use the technique of the fundamental connections to help us in different formats, from the graph x-intercepts to the zeros to the solutions, all leading to the factors, so that we can then find all the zeros. Because part of our goal in the overall scheme of things is we're going to be asked to find the zeros of a polynomial and write it in factored form. So we're going to be doing both of those, and today I'm going to show you examples from start to finish on what will be required of you for this class. So here's the division algorithm we talked about on the division video. I can take, if I'm going to divide two polynomials, f and d being called the divisor, then the function f can be broken up into the divisor times the quotient plus the remainder. And if you think back, this is what you did back in grade school. You divided long division, you got a number up on top, you may or may not have had a remainder, and so that's what this is referring to. When the remainder is equal to 0, or the degree of the remainder is less than the degree of the divisor, that's when you know you're done. Division can be used to factor a polynomial, because if the remainder is 0, then I end up with just a polynomial. The polynomial f is just a product of two other polynomials, which is what factored means, to write as a product. So one technique that you can have to help you find this out and to divide is long division of polynomials. So here's an example that I've prepared with the steps involved. I'm going to walk you through what I did each and every step of the way. Again, remember, this video on this is in more detail. I recommend that you watch it. So here is the function I'm going to divide. This is called the dividend. This is the divisor. This is the number you're going to divide by out here. And the very first important part of the setup here is to remember that you want your polynomials to be from the highest degree downward, and that all the terms must be present. So if you look in this one right here, you can see that there is no x squared or x term. So those are missing, but we need to put them into our problem because we want to have them as like placeholders, so that we know that they're there, so I can combine like terms and things. So we use 0 times x to whatever power is I need. So that's what I did there. The next thing it says is divide the first term of the dividend by the first term of the divisor. So you're only looking at the 2x squared divided into 2x to the 4th. So what times 2x squared gives me 2x to the 4th? Obviously x squared, and I put it up here above the x squared column. You'll notice that all my x squareds are basically lined up. Just like in grade school, when you put a number up, you multiply it to the divisor out front. So this x squared multiplies to all three of these terms, and we write it down underneath. You'll notice there's a couple of signs here because that's the next step. What we're supposed to do next is, in grade school, you subtracted, but here this is a polynomial. So to subtract a polynomial is basically what we have here is we had minus, and then this polynomial that we had. When you multiply this x squared to everything out here, we got this. And it has to be in parentheses, but we didn't put parentheses up in here. We don't. So how do I make sure I get this sign correct? Because I want to subtract this polynomial from that one right there. Well, I have to distribute this negative sign. So instead of writing all this and doing that, just remember to do this little phrase right here. So you multiply it around, you got this right here, and then you draw the line, change all the signs, and so I changed all the signs of that polynomial. And I exaggerated so I know that if I get distracted, that I've changed it already. I don't erase, I just write over the top minus signs, so I put big minus signs there. And then I just simply add in column form. So that's 0, a negative x to the third, plus a negative x to the third is a negative 2x to the third, and so forth and so on. So once you've done you added the opposites here, then in grade school you brought down the next number, but in polynomials you bring down everything. And then you just repeat this process until you get down to the remainder, and that degree is less than this one over here, then you know you're done. And in polynomials, remainders are written in fraction form. So here's the quotient, x squared minus x, and it's always plus the remainder over the divisor. So always put a plus. Even if this thing has minus signs here, it doesn't matter. Put plus, and then this on top, the divisor on the bottom. And that's how you write your answer. That's long division. We're going to be using that to help us find factors. The other technique we're going to use to find factors, I'm going to talk about right now. Again, I talked about this in another video for synthetic division. So we use the remainder theorem, the concept that we just talked about there. And this remainder theorem works two ways for us. One, it allows us to do synthetic substitution, which I discussed in the other video. And the other one, and then for this one, is we use it to confirm that we actually have a factored polynomial. So if a polynomial is divided by this factor right here, it's a linear factor, it has to say x minus a number, then the remainder is the value of the function at that k. Well, okay, that's important to know because we can use it a couple of ways. Like I said, if that remainder, f of k, is 0, then I knew that this factor, this thing right here, divided the polynomial evenly. So this becomes a factor. That's how we're going to use it the most. The second way is like what I talked about as evaluating a polynomial. And again, I did that in the other video, and you can see that and how that can be done. So synthetic division is basically a shorthand version. It only works when you're dividing by a linear factor, x minus a value. It does not work for any other technique, any other polynomial that you're dividing by. It has to be linear. And what we do is we take a polynomial in standard form. We take all the coefficients and place them in an upside down house, 2 layers deep. And then the number that makes that 0 goes out in front, which is called the 0. You bring down the first term, and then you do a series of multiplication, and then add. And then you multiply, write the answer here, and then add. And so that's what I have written over here. The setup is just as important. It's more so important than the other one. Here, all the terms must be represented by a 0. You cannot have any vacant terms. There has to be a 0. If you miss the 0, you will get the answer wrong. Even if there's no constant, you got to put a 0 for the constant. All terms must be represented. And I go into this a little bit more and show some examples in the other video. What we're trying to use the synthetic division for is to help us factor. And so we're looking for when that remainder is going to be a 0. When that remainder is a 0, then that is a factor which makes the k a 0 of the polynomial, which is what we're trying to find. So here is some things that we're going to use to help us determine what numbers to put out here. Okay? And this one is called the possible rational zeros. The possible rational zeros is a list of numbers where if a polynomial has the rational 0, then it will be generated by the list. A rational 0, remember, is a 0 that can be written in fraction form. And this is kind of tied to the technique you had when you did Algebra 1 for factoring techniques, where you took the number in the front and you found its factors, and the numbers in the back and you found its factors. Okay? And so that's the technique kind of here. The Possible rational zeros, the PRZ, is a fraction where the top numbers are the factors of the constant and the bottom numbers are the factors of the leading coefficient. And so you're going to divide every factor of the constant by every factor of the leading coefficient. So you're going to get a list. In that list, each number you do is also going to have a plus or minus in front of it. So this is what you're going to be doing. I'm going to show you some examples of this. I'm going to walk you through one now from start to finish on what it would look like on a test. So here we go. On a test, I'll give you a polynomial. I'll ask you to graph it, identify the end behaviors, find and label the extrema, list the possible rational zeros, find the zeros, and factor completely. So this is what a test question will ask you to do. Now, for time's sake in this video, I've already done the graphing part. Since I have shown you a video on how to graph, you can go look at that and see all the things that you can help you graph this thing out, labeling the maxes and the mins, and any integer x-intercepts, because those will be important to us. So the next step again is a repeat, is how do I identify the end behaviors? We can look at the degree, which is 3, the leading coefficient, which is positive, but we also are looking at the graph itself, so we can see clearly that on the right side, so the limit as x goes to the right of this polynomial, the y values are going up. And the left side over here is going down, so the limit as x goes to the negative infinity, or the left, of this function, and those are going down. So those are the two end behaviors for my graph. Find and label the extrema. So on the calculator, we went through and we found the relative minimum, the relative maximum, labeled it to 3 decimal places. Label it to 3 decimal places, please. Okay? So the next one is, what is the list, our PRZ? So for that, I need the factors of 5 and 42. And here's how I do that. PRZ. So it's going to be a fraction. The top numbers are the factors of the constant 42. So what numbers go into 42? 1 does, 2, 3, 6, 7, 14, 21, and 42. Quite a few of them. The numbers that go into 5, 1 and 5. So I do that part first, and then the next thing is this. Each of these numbers in here has to get divided by 1, and then each of these numbers up here has to be divided by 5. So the list is going to get pretty long because of this. We have quite a few factors, but that's okay. This is how you do it. I take all the top numbers and rewrite them because they're being divided by 1. So I have a 1, a 2, a 3, 6, 7, 14, 21, 42, comma, and then I'm going to take them all, because I write on a rule here and they're right underneath, divide all of them by 5. So that gives me 1/5, 2/5, 3/5, and so forth. Now, when you're doing this and generating these lists, don't repeat values. So if you do this and you repeat a number that you already have listed, you don't need to list it twice. Once I have it like this, I just usually go back and put a plus or minus in front of all of them, because that's how many numbers are possible. So, and plus or minus. And so you can see, although this seems like a long list, remember this came from the fact that when this was developed, they did not have calculators to graph it or anything like that. So they had to devise ways to limit the number of choices that we're looking at, because they couldn't just do every single value that's there. It's just way too impossible. This is your possible rational zero list. What this means is, if there is a rational zero on this polynomial function, then it will be in this list. And I can show you real quickly right here that we can see up here when I graphed it, and that we always want to label any x-intercepts that are integer values. I have a 3 here, and 3 is in my list. I have a -2 here, and -2 is in my list. There's a third 0 in here, right here, Okay, and that number right there, although I don't know what it is also in my list. And so we can see from this graph that it's between 1 and 2. So I know already that any value that is not between 1 and 2 is not going to be a 0. So this helps me then eliminate some choices. And that's how we use the possible rational 0 to help us kind of narrow down some possibilities that might be beneficial to us. Now, once I've done all this, the next thing you want to do is start confirming that you actually have these zeros. Although on a graph it looks fine, we know that there is hidden behavior. Okay? To me, when I wrote this, it just looked like you went through 3, 0. And so I marked it as 3, 0. If it wasn't, maybe it's like 2.9991625. Well, that's not 3. And so that I need to confirm that 3 is actually a 0. To do that, I use synthetic division. Synthetic division will do two things for you. It will confirm that a number is indeed a 0, and it will factor the polynomial as you go. Here we go. We're going to set it all up. I'm going to test the 3. I'm going to do synthetic division. I need 2 rows. The coefficients are 5, negative 12, negative 23, and positive 42. 5, negative 12, negative 23, and 42. And as I showed in the video, the last one down here gets a box underneath. This is where the remainder is going to go. And if all goes well, that number will be 0. Synthetic division is the first number comes straight down. And then we multiply. 3 times 5, 15, and we write it underneath the next number. And then we add these. A negative 12 plus 15 is 3. And repeat. 3 times 3 is 9. You write it underneath. And then you add these up, and you get negative 14. And then you multiply those numbers right there, and lo and behold, you get negative 42, and the remainder is 0. So what does this mean? So I have now confirmed that that is indeed a 0. So x minus that 0 is a factor. And not only that, but you've actually factored this polynomial already. F of x can now be rewritten as x minus 3 times these numbers are the coefficients of your remaining factor. So it's this times the polynomial created from this, which is 5, this is constant, x squared, so 5x squared plus 3x minus 14. See, now it's in factored form. It's not completely factored. Okay, we're going to test another one up here. The negative 2 we think is a 0 also. And so instead of going back and starting again, you can actually stack these. This is what I recommend. So just continue the synthetic division this way. Remainder box underneath the negative 14, and try negative 2. If it works, I'll get a remainder of 0 and a continued factoring. Synthetic division is bring down the first number, multiply, that's negative 10, add, that's negative 7, multiply, it's positive 14, and sure enough, negative 2 is 1. So that means that x minus a negative 2 is a factor. And we can now continue the factoring of f of x. There's the x minus 3. Now I have this factor, which is x minus a negative 2. And then this are the coefficients of the remaining factor. That's the constant, that's the x term, and I get 5x minus 7. So this right here is factored. Okay? If you stopped right here, and you can even say it's factored completely. Now, in the next lesson, I'm going to show you that we're going to take it a little bit farther than that. Okay? Actually, I'll show you right now. This is factored in linear factors, but we want all the factors to look like x minus a number. So we want them to easily display the 0. So we can look at this over here, and we can see there's a number between 1 and 2. Down on my list, the numbers between 1 and 2 is 6/5 and 7/5, positive versions of it. But in the factors, I can see that there's a 7 and a 5. So I know it's going to be 7/5. What if I continue this process with 7/5? Well, that's easily done. Bring down the 5. 7/5 times 5 is just 7. And there you go. So all of these are zeros. So all of these are zeros. Okay. And this down here is always the remaining factor. So you can't forget it. So the complete factorization of f of x would look like this in linear factored form. That 5, which by the way, if you haven't noticed, is always the leading coefficient. So to be the leading coefficient times x minus 3, x minus a negative 2, and x minus 7/5. And that is factored as a linear factors right there. Now, that's factored form. You also want to list the zeros. We know the zeros are there, but you're going to list it in this fashion. Write zeros and a colon, and then give me the list. 3, negative 2, 7/5. The order in which you write them does not matter. And so we have done what will be asked of us on the test. Graph it. Extrema is listed in behavior. Create the possible rational zeros list. Confirm that these are indeed zeros. List the zeros. Write it in completely factored form. This is what will be asked of you on your test as a test question. Okay, I'm going to show you another example that does something a little bit differently, a little twist on this scenario, and that's this problem right here. We're going to graph it on the calculator, which I have already done. Pull it up here. So there's my graph. Get that glare out for that. So we got all these little things here. You can see that it has 3 x-intercepts. So we know there's going to be 3 real zeros. I'm not going to draw the graph or do that, but I'm going to list the possible rational zeros. So our PRZ. And we need the factors of 6, which are 1, 2, 3, and 6. And then the factors of 1, which are just 1. So this one's a little bit easier list to generate. And I give you plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So if it has rational zeros, it's one of those numbers. So somewhere in here is going to be one of those numbers. And we can use that to help us determine which one we might want to try first. Okay? So looking at this calculator, the scale goes from negative 5 to 5. If you look closely, this one does not go through a mark. Okay, so that means it's not an integer. This one does not go through a mark. Sometimes it's harder to see that. It kind of looks like it does. But this one does. So there's a number right here, which is a rational zero. Right there. And so since I don't have any fractions, it has to be one of those numbers. And since I'm on this side over here, it has to be a negative 1. And it doesn't look like that's negative 5. It doesn't look like negative 1. It doesn't quite look like negative 2. It can't be negative 6. So I'm guessing it's probably negative 3. So that's what we're going to try first. I'm not positive it's negative 3. I mean, it could be something else. But I don't know. Let's find out. So I think it's a good guess. So how do I confirm something? Well, we use synthetic division. If it is a 0, then I'm going to get 0 as a remainder. So I got a 1, a negative 8, and a negative 6. And bring down the first number, multiply, add, multiply, add, multiply. And sure enough, negative 3 is indeed a 0. So I know at this point that f of x can be written as x minus a negative 3. And then these are the remaining factors right here. So this is x squared minus 2x minus 2. So based off of my graph, okay, none of these other numbers are going to be those zeros. And so there also is, there's no fractions in here. So what is this telling me? It tells me then that those zeros are not rational zeros. Well, if they're not rational zeros, what kind of zeros are they? They still cross the x-axis, so they have to be real. And then we go back to our knowledge of real numbers are broken up into two groups, rationals and irrationals. The zeros from this polynomial right here are going to be irrational zeros. Okay, so I cannot confirm with synthetic division. This part is now done. This is a quadratic. So how do I get the zeros from this if I can't factor it? If I can't confirm it from the synthetic division? If I can't do any of those other things? Well, we have to go back to Algebra 1 techniques, and we have to look at this as, well, I know solutions are also considered zeros and part of the x-intercepts. So we take that right there, 2x minus 2, set it equal to 0, and solve this. Now, we're not even going to try to factor because we know it can't factor. So the only option I have left is the quadratic formula. We solve this equation by the quadratic formula. X equals a negative b plus or minus the square root, b squared minus 4 times a times c, all over 2 times a. And we plug our numbers in there. A is 1, c is a negative 2, d is a negative 2, and so there's the plug-in. Doing all the manipulations and solving and all that kind of stuff and simplifying, we get down to this part right here, which is 2 plus or minus 2 times the square root of 3 over 2. And you want to simplify this. You need to simplify these. Split them up into two pieces, like an A and a B thing. And this right here becomes, so this will be 2 over 2 plus or minus 2 root 3 over 2. The 2's will reduce in each fraction, and I get 1 plus or minus the square root of 3. These two numbers right here are the solutions to this equation. So that means they are also the zeros. I can now list my zeros as, don't forget this one, negative 3, comma, and you can write this as like this, where it's 1 plus the square root of 3, 1 minus the square root of 3, or you can separate them. Okay, I can write it as 1 plus the square root of 3 and 1 minus the square root of 3. Or you can write it together just like that, 1 plus or minus the square root of 3. So there are 3 zeros here, confirming that we had 3 x-intercepts. So how do I go from these zeros then to factored form? Okay, well, it's each of these zeros in a linear factored fashion, and we have a leading coefficient of 1, so I know that I'm going to have a 1 out in front. So it becomes x minus a negative 3 times x minus, now I need to write that. So what I want you to do is I want you to write it as x minus, and then put a little parenthesis, 1 plus root 3, close that, close the big one. Open the next one, 1 minus the square root of 3, close and close. That's how I want you to express your answer, please. Just like that. So this is what's going to be asked of you for homeworks and also for tests. So that ends 3.4.